Hello everyone, I'm Yuanpei. It's my pleasure to introduce our work, OS rendering service made parallel with out-of-order execution in order commits. This is a joint work by iPads, Shanghai Jiao University, and Fields Lab, Huawei Central Software Institute. Smart devices like smartphones, pads, laptops, etc. have become an important part of our daily life. And the OS rendering service behind powers such stunning graphical user interfaces. But the landscape of smart device is changing rapidly. The recent wave of foldable smartphones, foldable laptops, and one-chip multi-screen setups in cars and smart homes dramatically amplifies the rendering workload. For example, a trifold phone, often using a chipset similar to its single-screen counterparts, need to render 117% more pixels per frame. This creates an enormous demand for rendering scalability. And this demand is continuous. Displays are constantly evolving to become more immersive with larger screen areas, clear with higher pixel densities, and smoother with higher frame rates. The figure on the left shows the number of pixels flagship smartphones need to render per second since 2010. However, the performance of the underlying rendering service often becomes a bottleneck. This compels manufacturers to make difficult trade-offs. As shown on the right, some manufacturers reduce pixel density on their foldables, sacrificing the definition, and some lower the frame rates from 120 Hz to 90 Hz, impacting the smoothness. So what is the root cause of this bottleneck? We made two observations. First, CPU bottlenecks OS 2D rendering. We analyzed various common smartphone scenarios. On average, CPU accounts for 82% of the frame rendering time. The GPU's workload is much shorter and can run asynchronously with CPU. So the overall frame rate is dictated by the CPU rendering time that involves computationally intensive tessellation and triangulation, glyph rasterization, and other GPU object preparation. Given that the CPU is the bottleneck, the obvious solution seems to be using more CPU cores. But this leads to our second observation. Multi-core utilization is severely limited in the current rendering service. This chart shows the CPU core utilization on a 12-core chipset during rendering. One core running the render thread is almost saturated. Meanwhile, most of the other cores are either idle or significantly underutilized. The current predominantly sequential rendering model fundamentally prevents the system from taking advantage of the powerful multi-core processors available in modern chipsets. Based on two observations, we argue that the next generation rendering service should adopt a parallel architecture to address the scalable rendering demands, particularly as Moore's law slows down, which restricts single-core performance. There have been some prior efforts at parallelization, such as interframe parallelism, where different stages of consecutive frames are pipelined across a few threads, and multi-window parallelism, where different windows are rendered in different threads for later window composition. However, these cross-grained methods do not scale. Interframe parallelism can span at most 2 to 3 threads with load imbalance and introduce more latency, while multi-window parallelism has applicability limitations, as usually a main app with a single window occupies the entire workload. It also has extra memory and composition costs. We wish to enable much finer-grained parallelism within a single frame, utilize more CPU cores, and deliver high frame rates even under constant heavy loads. Before we dive into our solution, let's quickly review how a typical OS rendering service works in iOS or OpenHarmony. This will help clarify the specific challenges we need to solve. Rendering service is an OS system service, renders the screen content synchronized from different applications in a unified manner. At the heart of the service is a unified render tree. It manages all the drawing information on the screen. Specifically, each render node may contain some draw commands. Native applications synchronize these draw commands to the rendering service, which populates this tree. For example, the app here shows a blue card represented by the subtree with 3 render nodes and 4 draw commands. A key point to note is that each render node on the tree only contains the relative information R with respect to its parents, such as the relative transform matrix encoding translation, scaling, and rotation. This design ensures that modifying R of any node efficiently updates the entire subtree, for example, moving its position. Also, it should be pointed out that the join order must be respected for correctness. Node join is not always commutative due to possible overlapping. For example, the blue card must be rendered before the red circle and the red X. In the render tree, each render node has its children sorted based on the join order from back to front. According to this definition, to render a frame, the system performs a sequential depth-first traversal of the tree that implicitly enforces the join order and invokes the underlying 2D engine to convert a stack of relative information into absolute states. As the tree is traversed, each abstract jaw command is translated by the 2D engine into concrete GPU objects like meshes, shaders, and pipelines, which are later sent to the GPU for pixel rasterization. This translation is the CPU-intensive work we identified earlier. While Vulkan exposes a stateless interface for parallelization, current 2D engines utilize stateful APIs, while states are kept internally in the 2D engine, so new jaw commands can rely on past jaw commands. To summarize, designing a scalable OS rendering service with fine-grained parallelization faces 3 key challenges. First, state dependency. Parallel tasks need complete and absolute states, but the render tree only stores relative information, which seems to demand a sequential traversal. Second, join order dependency. During rendering, we must respect the overlapping relations. A parallel execution could easily break the required join order. Third, interface dependency. Parallelization is inherently stateless. While current 2D engines utilize a stateful API for custom rendering applications and internal stateful optimizations like command batching, a new parallel model must maintain compatibility as well. To solve these challenges, we drew inspiration from a classic powerful concept in computer architecture, out-of-order execution and with in-order commits. Modern CPUs achieve incredible performance by analyzing instruction dependencies, executing independent instructions in parallel and out of order, and then using a reorder buffer to commit the results in the original program order to ensure correctness. We saw a clear analogy here. A draw command is like a CPU instruction. The multiple CPU cores are like the various execution units. State dependency is like an operand dependency, and the join order is the program order. So our key insights is to adopt the same winning strategy: in-order preparation, out-of-order execution, and in-order commits. These insights led us to the design of Sparse, a new scalable and parallel OS rendering service. Sparse redesigns the rendering procedure into 3 distinct stages, as the timeline illustrates. First, on the main thread, we have a fast, lightweight in-order preparation stage. Second, the bulk of the work, about 76% of the total load, happens in the out-of-order execution stage, with a pool of worker threads executes rendering tasks in parallel. Finally, a dedicated commit thread performs the in-order commit, gathering the results and ensuring rendering correctness. Let's see how this design addresses our first challenge, state dependency. Well, nodes only store relative information. During the in-order preparation, Sparse traverses the render tree once in a dry run without doing any rendering. Sparse calculates and records the absolute information A for each node, relative to the screen coordinates or the absolute 0. A is stored within the nodes that contain jaw commands and can be reused across frames until an animation or an interaction updates its value. With this absolute information, during the same traversal, Sparse can now encapsulate truly self-contained rendering tasks. Each task can batch multiple jaw commands if possible, and has their complete states. These tasks are then put into a single producer multi-consumer task pool, ready for the worker threads to consume in parallel. For the second challenge, join order, how do we execute these tasks out of order but still get the final image correct? During the preparation stage, in addition to creating tasks, sparse also explicitly constructs their overlapping relations by chaining them together for a naive join order and managing their join regions through axis-aligned bounding boxes for each task. The chain is later synchronized to the commit thread from the main thread. With self-contained tasks ready, we move to the execution stage. Worker threads simply pull tasks from the pool and execute them in parallel and out of order. Since they are dependent, any thread can process any task with any order. The output is a set of GPU objects packed together and sent to the commit thread. To support this, we built a new stateless 2D join engine named Spate2D. Spate2D accepts self-contained randoming tasks and provides thread-safe management of GPU resources like buffers and pipelines, which is crucial for conflict-free parallel execution. Please see our paper for the details. This brings us to our third challenge, interface dependency. Sparse solves this by decoupling the rendering procedure into two phases. We provide a stateful API layer that is fully compatible with existing custom rendering applications and state-based optimizations. Internally, this layer translates our familiar stateful commands into self-contained stateless tasks, which are then processed by Spate2D. This gives us both the compatibility and parallelism. And finally, the in-order commit. In-order commit thread receives completed tasks, namely the generated GPU objects from the workers. Using the overlapping relations that the main thread generated earlier, it ensures that if two tasks overlap, the background task is always committed before the foreground task into the GPU command. This process is very lightweight and is almost entirely covered by the execution stage. Lastly, we present the evaluation. We implemented and evaluated sparse on a range of modern commercial smartphones, specifically the single-screen Mate 70, dual-fold Mate X5, and tri-fold Mate XT, as well as multi-screen configurations. The chart shows the frame rendering time across 42 representative scenarios under different setups. Compared to our sequential baseline, sparse with 5 workers improves the frame rates by an average of 1.76 to 1.91 times, achieving a stable 120 Hz in many scenarios while the baselines could not. Sparse achieves this by making much better use of the hardware. Here, you can see how the workload, which was bottlenecked on a single core in the baseline, is now much more balanced across multiple cores with sparse. This efficiency translates into two key benefits. First, under the same frame rates, sparse can reduce the device's total power consumption by 3.0%. This is because a balanced core utilization can make DVFS to apply a lower overall voltage and frequency, whereas rendering a single core in the sequential baseline often forces the CPU to raise its frequency for frames to meet their display deadlines. Alternatively, within the same time budget, sparse allows us to render 2.31 times as many graphics primitives, giving designers far more freedom to create richer and more appealing user interfaces. To conclude, we present sparse, a next-generation, scalable, and parallel OS rendering service. By drawing inspiration from out-of-order execution and in-order commits in CPUs, sparse untangles state dependency, join order dependency, and interface dependency. Evaluations demonstrate that sparse substantially enhances frame rates on emergent foldable smartphones and multi-screen configurations, efficiently leveraging multiple CPU cores while reducing power consumption and scaling the number of graphics primitives. We believe that this design offers a clear path toward building scalable rendering systems for the future of smart devices. Thank you all, and I'm happy to take questions.